Yeah, good afternoon all. Thank you all for joining. And today we have the fifth talk of our ongoing talk series on. Today's speakers are Prof. Srinath, Srinivasa and Ms. Jayati Deshmukh, both from our own institute. They will be speaking on the topic Computational Transcendence, Responsible Agents. Ms. Pooja Basin is the session chair for today's talk. She is a PhD student at the Web Science Lab, IIIT. Without further delay, let me hand over the stage to Ms. Pooja.
Thank you, sir. I'll start by introducing our speakers for the day. Professor Srinath Srinivasa heads the Web Science Lab and is the Dean R&D at the International Institute of Information Technology, Bangalore, India. Professor Srinath holds a PhD from Berlin Brandenburg Graduate School for Distributed Information Systems, an MS by Research from Indian Institute of Technology, Madras, and BE in Computer Science and Engineering from the National Institute of Engineering, Mysore, India. His research interests are in understanding how the World Wide Web is affecting humanity and how can the web enable social empowerment and capability building. He has participated in several initiatives for technology-enhanced education, including the EduSat program for the Visvesvaraya Technological University, the National Program for Technology-Enhanced Learning, a Switzerland-based online MBA school called Educatis, and IIITB's educational outreach program with Upgrad. He has served on various technical and organizational committees for international conferences like International Conference on Weblogs and Social Media, ACM Hypertext, International Conference on Management of Data and Data Science, International Conference on Ontologies, Databases and Applications of Semantics, International Conference on Big Data Analytics, etc. As part of academic community outreach, Professor Srinath has served on the Board of Studies of Goa University and as a member of the Academic Council of the National Institute of Engineering, Mysore. He has served as a technical reviewer for various journals like the VLTB journal, IEEE Transactions on Knowledge and Data Engineering, and IEEE Transactions on Cloud Computing. He has also served as an associate editor of the journal Sadhana from the Indian Academy of Sciences. He is also the recipient of various national and international grants and awards from foundations and companies like EU Horizon 2020, UK Royal Academy of Engineering Research Councils UK, MIT, DST, Siemens, Intel, Emphasis, EMC, and Guru. Our another speaker for the day is Ms. Jayati Deshmukh. She is a PhD research scholar at Web Science Lab, IIIT Bangalore, under the guidance of Professor Srinath Srinivasa. Her research interests broadly lie in the area of artificial intelligence and specifically in autonomous systems, multi-agent systems, network science, and game theory. She holds MTech in data science from IIIT Bangalore and BE in computer engineering from Gujarat Technological University. She's a gold medalist in both undergraduate and graduate degrees. She has 4+ years of work experience at Accenture Technology Labs, Bangalore, where she did research and development in the area of natural language processing, deep learning, and knowledge graphs, which resulted in many successful POCs as well as patents and publications. Over to you, Professor Srinath.
So firstly, thanks once again for inviting us for this talk. This work of ours is particularly close to how we work in our lab, and has basically pertains to one of the pressing problems of today, that of AI ethics. Right? As we know, more and more artificial intelligence is leading us towards autonomous artificial intelligence. That is, AI agents that can act autonomously without even probably a human oversight, and make a lot of decisions on their own. Of course, one of the biggest examples of this is the increasing technology in autonomous driving, autonomous cars, and so on. But autonomous agents are used in several different places for managing very complex systems. Now, as autonomy becomes our autonomous decision making becomes more and more ingrained into our technological landscape, the idea of AI ethics becomes very important, especially responsible autonomy, right? And see, ethics by itself is a very philosophical topic. There are several schools of thought about what is ethical and so on. While there is a lot of research happening around the notion of ethics, for example, Asimov's laws of robotics and so on, there is a much more closer or immediate need, that of responsible AI. That is, even when we know, for example, what is an ethical thing to do, are sure that an agent acting autonomously will actually do that, right? And so for that, we look into different kinds of models that are there for autonomous ethics. Firstly, we look at what is meant by autonomy in the first place. When do we say that some agent is acting autonomously, right? Currently, the best understood definition of autonomy is when autonomous choice or autonomous actions reflect what is called as rational choice or rational decision making, right? And so rational choice in turn is dependent on or defined by what's called a self-interest function. So there is a self-interest in terms of what an agent wants to achieve or what the agent prefers, whether this prefers A or B and so on. And utility maximization. That is, what kind of strategies does the agent use in order to maximize the utility towards self-interest, right? And so, given the self-interest and utility maximization kind of approach, can we be sure that agents acting autonomously will also act responsibly, right? And so there are a variety of use cases to show that this is not the case. You must have heard of this class of problems called the trolley problems. If you're in a trolley and there is a fork in the rails, and there are some workers working there, what will you do, and so on, right? And so there are a variety of these issues around or scenarios to tackle what are called this ethics or responsibility when it comes to autonomous decision making, so, right? And but from what we are arguing is that most of the current approaches towards ethical AI or autonomous AI basically try to impose ethics as a separate dimension, right? For example, there are approaches, robotics-based approaches, which are based on reinforcement learning, right? Where the environment primarily provides some kind of positive or negative reinforcements based on an agent's action to veer it towards acting more responsibly, right? And the problem with externalized notion of ethics is that ethics primarily becomes a question of nurture. That is, without an external nurturing environment or conditioning environment, we say that agents, self-interested agents, cannot be ethical and so on, right? And there are a few other approaches which use some kind of new dimension towards ethics. For example, an ideology. For example, you can tell an agent that act in self-interest, but always uphold certain virtues, right? Like kindness or like Asimov's laws, right? Don't harm any humans. So there are certain virtues you can uphold, but other than these virtues, you act in self-interest and so on, right? And now, even here, what we are basically saying is that ethics is something that is separate from self-interest, right? That's something that needs to be introduced separately from self-interest and so on. Okay. But if we look at human history itself, for example, you see that humans and many animals even have an innate notion of ethics, right? See, what we consider social norms or what is ethical and so on have not been imposed to us imposed on our population by some alien population, right? It's not an external entity that has imposed a notion of ethics on us. It's something that has emerged from individual dynamics, right? Individual self-interest dynamics and so on, right? And so in this work, what we are trying to argue is that there's an element of innateness in acting responsibly. And really, if we get this model correctly, then there should really be no conflict between acting responsibly and acting in self-interest. And so, okay. Fortunately, existential philosophy has a lot of work in this area, especially Indian philosophy. In fact, we often keep alluding to Sri Ramakrishna's saying. Once somebody asked Sri Ramakrishna, how should we treat others, and so. Okay, the common approach towards treating others or acting ethically is what is called reciprocity. So which goes like do unto others as you would have them done unto you, so right, and that is treat others as you would like to be treated, and so. Okay, but Ramakrishna basically said there are no others, right? So what he really meant is that the key to our concept of ethics lies in our sense of self. That is, where does the boundary of our self end? Does it end with our body-mind complex, or does it include other things, and so on, right? And essentially, when you're really in some sense transcended, when you have a transcended notion of self, you're essentially, the entire universe is you. You feel that entire universe is you, and so on, right? And so if anybody suffers as a consequence of your action, it's not them who is suffering, it is you who is suffering, and so on, right? And so that is the idea of a transcendence notion of ethics, right? And so what we're trying to do is we're trying to see if we can endow artificial agents with such a notion, with the notion of transcendence, which we call computational transcendence, or also an elastic sense of self. Okay. So this is the background to this work, and I call upon Jayati to take over and then present the technical details of this. Over to you, Jayati.
So good afternoon, everyone, and thanks a lot, sir, for setting the context and introducing this topic of computational transcendence. We'll be looking at it in further detail. So this is the overview of the presentation. We'll start with a brief introduction to this topic. Next, I'll be introducing different ethical paradigms. So we'll be looking at utilitarianism, deontology, and virtue ethics. After that, we'll go back to computational transcendence and see in further detail how we formally model computational transcendence and see it in a couple of different scenarios. We have designed a framework where we can model this kind of ethical dilemma between choosing responsible versus irresponsible actions. So we'll touch upon this framework and also show the implementation of CT as well as these different ethical paradigms on that framework. After that, briefly, we'll discuss some preliminary results of application areas where we have tried applying CT. So we'll look at supply chains and traffic management, and finally, we'll conclude and present some of our future directions of the work. So with that, let's get started. So yeah, as we all know, right, autonomous agents are getting more and more common and prevalent into our day-to-day lives, starting with, let's say, chatbots to even autonomous vehicles, autonomous cars, and these days even we have autonomous military applications. So there are a variety of autonomous agents which are interacting with other autonomous agents as well as us humans. And thus it becomes very crucial and important that when these autonomous agents act in these kinds of systems, they behave in a responsible manner. So here we are trying to propose this computational model of responsible AI, and we would like to point out some of the characteristics which these kinds of computational models should have. So one is usually responsible behavior is introduced in autonomous agents in two ways. One way is using top-down approaches. So for example, we discussed using reinforcement learning or even rule-based systems where these kinds of paradigms are enforced on the autonomous agents, and they are bound, they are designed such that they should bound to act in that specific way, versus we have other alternate ways in which it's a bottom-up approach, where responsible behavior emerges as an outcome of the behavior of the agents into systems. So we would be talking more on the second kind of bottom-up approaches. Another characteristic is of non-monotonic systems, where responsible behavior, or even generally the behavior of autonomous systems, right? They shouldn't be fixed. They should be able to, as they evolve in the system, they should be able to update their models, update their logic, and thus that's why it should be non-monotonic. And finally, none of these agents operate in isolation. So like we saw, in most scenarios, these autonomous agents will act with other autonomous agents as well as human beings. So in these kinds of multi-agent scenarios, the agents should have the capability to act in a responsible manner. So next, let us have a quick look at different ethical paradigms. We'll start with utilitarianism. So utilitarianism basically focuses on what is the net utility of all the stakeholders in the system for a given action, and agents will choose an action which maximizes the utility for all the stakeholders. Here the benefit is that there's no everyone is treated the same, so there's no elitism, no one's utility has a higher weightage. And usually if we see in different day-to-day scenarios, right, utilitarian models are how policies are designed. So for example, food distribution systems, if we see food is first given to people who are the poorest or who need it the most. Even in our recent vaccination policies, right, we noted that people who were at most risk were given the vaccines first, and so on. So usually we take this utilitarian approach. However, there are some challenges. So how do we exactly compute the utility of all the stakeholders when we do a specific action? Or even sometimes it might be difficult to know in advance what will be the consequences of the action of an agent. So next model which we would touch upon is deontology. So deontology is basically focuses on whether the agents are following specific rules or not. And they are not concerned so much about what were the consequences or results of those rules. So in this context, Kant proposed a variant of deontology where he introduced these two imperatives. So first imperative is called categorical imperative, where by which he says that the actions should be such that if it becomes a universal law, even then the system is fine. And second is practical imperative, where basically he says that we cannot use people as a means to achieve an end, right? But even in this model, there are some challenges. So one is like just to formulate in a specific scenario, right? What are the rules which would make most sense? That requires time and deliberation. So what do we do in scenarios where one needs to take instantaneous decisions? Then it becomes little challenging. And also, the agent should be able to handle contradicting rules. And the third model of ethics is virtue ethics. So basically here, the key goal here for the agents is that they should uphold specific virtues, irrespective of, again, what is in which context they are operating or what are the consequences of the actions. None of that matters. As long as they uphold a virtue, that is the way they operate. And agents usually strive to maintain a mean value of a virtue. So either of the extreme of any specific virtue is not good. They strive to maintain the golden mean, as it is called. And even in this case, there are a few challenges. So basically, first one is how do you exactly quantify? How do we measure what is a virtue? Secondly, every time you take an action, the agents need to like reevaluate, like is the virtue being upheld and not. And like deontology, again, there might be conflicting virtues which should be handled by the agent. So let us quickly look at one example and it will make it more clear. So here we are talking about this healthcare worker And there are some challenging times, something let's say like a pandemic, and this healthcare worker needs to decide whether to stay at home or to go to a hospital and do his job. So let us see how different models of ethics guide us, right? So first one is utilitarianism. So here, basically, the utility in this context we can think of is saving maximum lives. So if the healthcare worker goes to the hospital, he is able to save most number of lives. So that way he'll choose to go to a hospital. Based on deontology, what the healthcare worker can do is basically get an opinion of other healthcare workers in the neighborhood, and based on what is the let's say opinion of everyone, aggregate those results and accordingly decide like how many days he should go and what to do and so on. So that's the deontology based approach. And finally, virtue ethics. So here the healthcare worker would try to uphold the virtue of care and would go to the hospital to treat the patients. So this is how like different models of ethics guide in making the decisions. So this table will gives a nice comparison of different models of ethics as well as the model which we are proposing. So as we discussed, consequentialism or utilitarianism looks just what is the output or what is the maximum utility for all the agents or stakeholders. Deontology checks if the rules are being followed, everything else is immaterial. And virtue ethics focuses on whether the specific virtues are being upheld by the autonomous agents. In this context, we have this fourth variant, the model which we are proposing called computational transcendence, where we'll show that with an elastic sense of self, responsible behavior will emerge it will be emergent characteristics, and they would be able to act in a responsible manner. So in the next section, we'll be discussing more on computational transcendence. So to begin with, right, let me start with presenting what do we mean by this responsibility dilemma, right? So in most scenarios, agents have the choice of choosing between two kinds of actions. First kind of action is individually beneficial for the agent itself. However, if we look at its long-term consequences or the impact of that action on the collective, then it imposes some cost. So this is the first kind of action. And second kind of action is where it might be individually suboptimal or costly for this specific agent itself. However, collectively for the overall system in which this agent is operating in, collectively it's good for the collective. So this second kind of action is what we are calling as responsible action. And what we will show is the model which we will be presenting soon of elastic sense of self of agents. With that, the agents will choose this second kind of responsible actions when they act in different kinds of systems. So let me next elaborate more on this notion of elastic sense of self, right? So when we think about human beings, right, we never consider ourselves limited to just our mind or body. We are very elastic, and depending in which context or scenario we are operating in, we can easily identify with different aspects in the environment. So for example, of course, we identify with our mind-body complex, but then let's say we also identify with our family members, our home, our family, and so on, right? And when we are operating, let's say in a professional setup, then we identify with our teammates, our office, our profession, and so on. And overall, at the highest level, we even identify with the world or the environment level. So we as human beings have this notion of elastic sense of self. And this is what we are trying to incorporate into autonomous agents as well. And next, we'll discuss how do we formally do this. So coming to defining what do we mean by transcendence, right? So transcendence is, can be defined as the capability of an autonomous agent to virtually extend its identity to different aspects, like let's say other agents in the system, a group or collection of agents, or even abstract concepts. And it can extend to these aspects to different extents based on the semantic distances, which we'll discuss. And computational transcendence basically is modeling of this elastic identity of agents. So here, I'd like to highlight on the notion of two kinds of associations, right? So first, there's rational association, where let's say one agent associates with another agent as long as it fulfills its rational motives. So as long as the agent gets a utility from that interaction, it makes rational sense to associate with another agent. So this is one kind of association. Another kind of association, especially in this model of transcendence, is the association of identity. So basically, like we saw, right, the agent identifies with these other aspects or other agents in the system, and considers those other agents within its sense of self in some ways. So what happens as a consequence is that the interest of those other agents become a part of the self-interest of this agent. And then with that notion of self, when it operates, we'll see that it leads to responsible behavior. So yeah, basically, yeah, there are these two kinds of associations. And in the model of computational transcendence, we are highlighting that in this case, the agents have an association of identity with other agents in the system. So more formally, transcendence can be described as follows. So the sense of self of agent A has following three aspects to it. First one, I denotes the identity objects. So basically, the set of things which the agent will identify with. These can be other agents, collection of agents, or even abstract concepts, right? Like we discussed. Next attribute is semantic distance. So basically, we set a distance to each of the object in this identity set I, and that becomes the semantic distance. And third attribute is gamma of A. So gamma represents what is the elasticity or transcendence level of the agent itself. Let's say a lower value of gamma denotes that agent is restricted to just itself as its sense of self, versus a high level of gamma denotes that this agent takes other agents or other objects into its account while operating in the system. So these are the three attributes of transcendence. And next, let us see how do we compute utility, right? So usually utility is what the agent itself will get based on a transaction in the normal setup. But a transcended agent gets utility a little differently, and this is what this equation shows. So let's say an object O in the identity set gets a utility of pi I of O. Then the transcended agent A gets a scaled utility gamma to the power D times pi I of O. So if the other agent gets a utility of pi I, then the agent A gets a utility gamma to the power D times pi I, because it is transcending to some extent to that other object in its identity set. So to compute the total utility, what do we do is we sum across all the objects in its identity set and then normalize. So what it represents, it I'll show in the next slide. So let's say the agent here in this example identifies with itself, its family, team, country, world, environment with different semantic distances. And then in this column, we vary the transcendence level of the agent. So what do we note here is that as the transcendence level increases, it is able to consider others more and more into its sense of self, which is illustrated in this pie chart. So here, if we see with a transcendence level of 0.3, what do we note is the agent sense of self, 70% is constituted by just itself, and rest 30% other aspects play a role. Versus at a higher transcendence level, let's say of gamma equal to 0.7, we note that now its weightage to itself is just 34%, and rest of the aspects get a much higher weightage. So basically, when the agent is operating at a higher transcendence level, it is in its sense of self, it is taking all these aspects with a higher weightage into account. So I hope, that clarifies what do we mean by transcendence and how the transcendence level varies and what does that mean in the system and so on. So next, let us see with an example of prisoner's dilemma, right? So prisoner's dilemma is a game which basically models this dilemma where agents can choose between responsible and irresponsible choices. So think of it like here there are two agents, player A and player B, and each of them have two choices. They can either cooperate or they can defect. So in this context, cooperation is the responsible choice and defection is the irresponsible choice. Now, when both of the players cooperate, they get, let's say, a payoff of 6 each. However, if you check from this matrix, right, what happens is as long as one of the player is cooperating, there's a rational incentive for another player to defect and get a higher payoff. But as a consequence, what happens if all the players start defecting in the system, then the system falls in this DD kind of state where it's a suboptimal state for the system as a whole. So here, what we can see is that for any scenario which we, one thing to note here is, although it looks like a game matrix, you'd think, where does it apply? So it is applicable in a lot of day-to-day scenarios. So let's say CC state, for example, represents where all the people are paying their taxes. So as long as everyone pays their taxes, the system is in this kind of state. And as long as everyone pays the taxes, there's incentive, like it makes sense for the one of the people to defect and gain the, let's say, benefits of good infrastructure without even paying their taxes. And if everyone thinks like that and doesn't pay the taxes, then the system falls into this DD kind of state. So basically, prisoner's dilemma can model a lot of real world scenarios like this. And what in any of the game scenarios, if we study, right, what we note is that in a one-shot game where the players are going to interact just once, there's no incentive for the player to cooperate. So what we see is that this DD is a Nash equilibrium. So basically, it's the mutual best response for the agents to choose to defect. So D strictly dominates C, and agents will choose to defect, right? So next, we will show how things change when we bring in a transcended agent in this prisoner's dilemma context. So let me point out how we compute utility based on the model of transcendence. So utility computation for, let's say, player A is done as follows. So given, so player A, what it does is AI denotes the utility it gets, and it also takes into account the utility of another player based on a given game state. So it takes into account gamma to the power D times the payoff of other player B of I, and we normalize it, and that's how we compute the utility. And coming to the plots, right? So this will make it more clear. So based on this utility computation, we compute the expected payoff of cooperation and defect, and we plot it as follows. So on the x-axis, we vary the gamma or transcendence level of the agents, and the blue line denotes the expected utility of choosing to cooperate, and orange line denotes the expected utility of choosing to defect. So if you see at transcendence level 0, what happens is what we saw in the prisoner's dilemma example, right? There's no rational incentive to cooperate. So cooperate is somewhere here, and players would choose to defect, as we discussed just in the previous slide. However, as we increase the transcendence level on this x-axis, the agents are now taking the other agent into more and more into account, right? They are identifying with the other player and then deciding how to act, what action to do, whether to cooperate and or to defect. And we see as the transcendence level increases, the probability to choose D, the expected utility of choosing C increases. And at transcendence level 1, we note that it exactly flips. So now at transcendence level, it makes as much sense for the agent to cooperate as it made to defect when its transcendence level was 0. So yeah, in the prisoner's dilemma context, like we show that how transcendence brings in responsible behavior of choosing to cooperate, right? So next, let us move on to the framework. Here, we would highlight the framework where we have tried to model this dilemma between choosing responsible versus irresponsible choices in a network setup. So what we begin with is we have a network like this, which is a simple undirected graph. And each node here represents an agent. And every agent is connected to some other nodes in the network, and each node we set its gamma or transcendence level, and the semantic distance is a edge property. So basically the semantic distance between two neighbors is denoted by the edge characteristic. So next, what we simulate is something as follows. So every agent can play three kinds of roles. The agent can act as a sender and send a packet to one of its neighbors, whom we call as the intermediate agent. And the intermediate agent should forward that packet to a receiver, which is the final destination for that packet. Now, we model the ethical dilemma as follows, right? So the intermediate agent here has two choices, basically. The intermediate agent can either choose to forward, which is a responsible choice. However, the intermediate agent incurs a cost because it is going to forward that packet. So let's say it will spend some energy and so on. And the irresponsible choice is to drop the packet. So basically, if the intermediate agent just drops a packet, he incurs no cost. However, the sender gets a negative utility because he intended to send that packet, but it wasn't sent by the intermediate. And this is how we model the system. And some of the metrics which we are tracking are as follows. So we see what is the average cost of all the agents which incur in the system. What is the utility they derive, which the senders, for example, will derive if the intermediate agent forwards the packet. A virtual utility comes from the transcendence. So if the sender gets a utility, the intermediate agent also gets the utility because it transcends to the sender, right? So that thing we are tracking in this metric called virtual utility. And the fourth metric is of burnout. So let's say if there is a threshold of how many messages an intermediate agent can pass, if the agent reaches that threshold, then we say that that agent has burnt out. So we are also tracking that as a metric. So given this framework, let me elaborate how do we compute the utility and cost metrics for the transcended agents. So here we'll focus on the choice of action of the intermediate agent I. If the agent I chooses to forward the packet, then the source gets a positive utility since it intended to forward the packet to the receiver, and the intermediate agent did that. So source gets a positive utility mu, and since this agent I is transcending to the source, it derives the utility gamma to the power d times mu, right? On the other hand, if intermediate agent drops the packet, then what happens is the source gets a negative utility minus mu. And since, again, like before, the agent I is transcending, even this one gets a negative utility minus gamma to the power d times mu. And talking about cost, if the agent I forwards the packet, it incurs some cost, whereas if it just drops the packet, then it doesn't incur any cost. So here, that's why we are saying there's this dilemma, like what should the intermediate agent do? Should it forward the packet, which is the responsible choice, or should it drop the packets, which is the irresponsible choice? And we'll show what happens when we vary, let's say, the transcendence level and so on. So like the prisoner's dilemma case, right? We compute the utilities, expected payoffs of both the actions as follows. So if the intermediate agent chooses to forward, then it gets it incurs some cost and it gets a scaled utility. And if it chooses to drop, then it gets a negative scaled utility. We pass this through a softmax function, and then probabilistically, based on that, agent decides whether it should forward or drop the packet. And after few iterations, it decides based on how its interactions have been with all different sources in its neighborhood. It decides how it should update its semantic distances, right? So what it does is it sees how much utility it is deriving from that specific source as compared to the total utility from all the sources, minus we say how much it has been, how much it has costed this agent for that interaction with a specific source as compared to all the sources. So we compute this, and then when we like scale it by a learning rate and update the distances after every few epochs. And once the system settles, then it kind of reaches the stable state, and then we simulate how the simulation works. We'll show some results next. So here, what do we do is on the x-axis, you can see we will vary the transcendence level. So when we set the transcendence level, that is the transcendence level of all the agents in the network. And then we see at equilibrium, what is the total cost, what is the total payoff, and so on. So here, what this plot shows us is that as we increase the transcendence level, the total payoff increases. So this is the real payoff which the agents get when they operate in the system. And this green line denotes the virtual utility. So basically, this is the utility which the agents derive when they transcend to other agents in the system. So we see that as the transcendence level increases, both the payoffs and the virtual utility increases. However, the cost also increases. So as it tries to operate at higher transcendence level, we see that it incurs a higher cost as well, right, while operating. And the final plot here shows is how many packets are forwarded or dropped. So similar to the prisoner's dilemma case, right? Initially, when the transcendence level is 0, a lot of packets are dropped, right? Since the agent is just thinking about itself, and why would it choose to forward the packet since it incurs it a cost? So most of the packets are dropped initially. However, as we increase the transcendence level, we see that the forward probability increases, and it almost reaches 1. So like at high transcendence level, almost all the packets are being forwarded in the system. In the variants which we discussed here, the system designers basically fix the transcendence level of all the agents in the system, and then the agents operate it. One more variant which we tried out was where the agents could update their transcendence levels based on their interactions. So what the agents compute is they find what is the net utility they have received versus what is the utility they have given. And if the environment is such that the utility which they have received is greater than the utility which they have given to the system, then in a way it motivates them to act in more responsible ways and so on. So we pass it again through a sigmoid, and then update the agents update their transcendence level as follows. So this plot on the top right shows how the transcendence levels are updated. So even when the initial transcendence levels are, let's say, set to 0, the agents are able to learn and update their transcendence level to somewhere around, let's say, 0.6. And we can see that as the initial transcendence level increases, even the final transcendence level where the agent settles at, even that increases in this plot. And another interesting thing to note here is that since the agents can learn, right, to operate at higher transcendence level, very hardly any messages are being dropped. And we can see that almost all the messages get forwarded in this kind of scenario. And the third scenario which we would discuss is of adversarial resilience. So far, right, what happened is all the nodes in the system were transcended to that level. And basically everyone acted in a responsible manner, and things were good in the system as a whole. So next, what we wanted to check was what happens when there are a few adversarial agents, where some agents are selfish agents, which are not transcending, which care only about their own self-utilities, and they're trying to optimize that, right? So what we did was we introduced like nodes with high degree centrality and made them as adversarial agents. And again, we got some very interesting results, which showed that the system is very resilient. So here, for example, we plot on the x-axis, we vary the proportion of adversaries, and on the y-axis, we vary the transcendence level of agents. And each square here basically denotes how many extra messages were forwarded by the agents as compared to the messages which it dropped. So basically, we would want more blues and higher values for this metric. So the plot on the left shows that as the adversary proportions for quite high adversary proportions, we could see some packets were getting dropped and so on. However, the plot on the right shows with gamma updates. So once the agents were able to update their transcendence level, we see that the drops also reduce despite a lot of adversaries in the system. So these were some results in context of the adversarial agents and the resilience of transcended agents while operating in these kinds of systems. So this was the first part. Next, what we did was we tried the different ethical paradigms which we discussed on the same framework, and simulated different kinds of agents. So, for example, first we tried making all agents as utilitarian, where they computed what was the net utility, total utility for a transaction, let's say between the source and the intermediate. And based on that, probabilistically, they decided whether they should forward or drop the packet. Similarly, we had a deontologic agents. So these agents surveyed their neighborhood and estimated what is the forward probability for the agents in their neighborhood. And based on that, they tried to adopt similar behavior. And the third kind of agents were virtue ethics agents. So here we made forwarding as a virtue, right? So what we did, the agents got positive virtue points if they forwarded the packets, and they lost virtue points if they dropped the packets. And agents tried to operate in the system such that they could optimize and maintain their virtue points at a specific threshold. So we made all the agents follow one of these ethical paradigms, and then we compared how things look like. So these are the results we got. So here, if we look at the first bar in all these plots, we see that it is the utilitarian agent. It is specifically targeting to optimize for the utility. And what we note is that it has the fewest drops. So it is dropping the least messages. And however, if we see, it is also burning out more. So it is reaching that threshold point the most. Next kind of agent is a deontologic agent, where these agents will try to learn what the other agents are doing in their neighborhood. So here we see that it is very sensitive to behavior of other agents in the system, right? So if even a few agents start dropping their packets, maybe because they burnt out or something, the others also try to respond to that, and that's why its utility is quite less. And they start dropping more in that kind of context. Third kind of agent is basically a virtue ethics agent. So here it tries to optimize for the virtue. It doesn't care about its utility or burnouts. And so it has still quite few drops as compared to others. And finally, we have this yellow one shows the transcended agent with just transcendence level 3.3. So even with a small level of transcendence, what we can see is that it is able to get a pretty good utility while operating in the system. And its drops are also like low, kind of, right? So we are doing some more experiments with different kinds of agents having different models of ethics, and that's in progress right now. Next, let me quickly touch upon a couple of preliminary results of CT applications. So first application is of supply chain, where let's say user 1 places an order for user 2 of objects A, B, and C. And similarly, user 2 places an order. And here we have warehouses, let's say, which have objects which store only one kind of object. So let's say warehouse 1 is only having objects of type A and B, and warehouse C has objects of only type C. So what the warehouses will do is they'll collect multiple orders from multiple stores and then decide when to ship it forward and so on. So specifically what we have, like formally, what is the change here is that in the model so far in that network context, it was a discrete prisoner's dilemma, basically, where the agents could choose either to forward or drop the packets. But here the decision changes. So here, since it's continuous prisoner's dilemma, so the decision basically where each intermediate agent needs to decide upon is whether it should forward the packets right now, or should it wait some time, collect more packets coming from multiple sources, and then forward. So that is the scenario we are trying to model in this context. And some preliminary show results give interesting results. So for example, we see that as the transcendence level increases, the average delay in the system is reducing. However, if we see the cost is increasing, since the intermediate agents choose to send out the packet sooner and so on. So the cost increases as the transcendence level increases. Second scenario is of traffic lights. So here what we tried to do was we take a scenario like this and make each traffic light as transcended traffic light. So I'll come to that. By that we mean that there are different kinds of traffic lights, right? So usually we have cyclic traffic lights where they'll just operate in fixed cycles and so on. Current times, we also have smart traffic lights where they'll, based on cameras, see how many vehicles have been waiting for how long, and based on that turn green, let's say for the road, which has a maximum waiting time. And here we are proposing a third kind of variant called transcended traffic lights. So basically, they can sense the traffic light in their neighborhood level. They can transcend to their neighboring traffic lights, and based on that, take decisions which ensures that the traffic flows are much more smoother at the network level. So again, some preliminary results. So here what we see is the average vehicular waiting time for the transcended traffic lights is lower slightly as compared to these other variants. And if we talk about the average vehicular speed, it is higher. But these are again preliminary results on artificial networks. We are doing like grid kind of networks. We are at the behavioral model level itself, we need to incorporate some more aspects to it and then run the experiments for more realistic networks and so on. So yeah, with that, I'll conclude here. So basically what we are proposing is this model of innate model of ethics, where the agents have an elastic sense of self such that they can take into identify with other agents in the system using this elastic sense of self. And what we showed in different kinds of scenarios was that it leads to responsible behavior in the system as a whole, even in like dilemmas or conflicting situations. Another point to note here is that at least in autonomous agents, right, it's easier to set at least some baseline level of transcendence in the autonomous agent. So that is implementation wise, that is easier. And finally, we saw that even in different kinds of application scenarios like supply chains and traffic management, it is giving some interesting and useful results there. In future, following are some things which we plan to do next. So yeah, like we discussed, we are doing some more extensive experiments on CT applications. Currently, the networks were fixed, but we could also extend it to dynamic networks like mobile ad hoc networks and so on. Currently, the transcendence, for example, was modeled to just neighbors one hop away, but in future, we could take into account other agents which are, let's say, multi-hop away and so on. So that is one thing which we want to explore. And finally, currently the transcendence has been only to other agents in the system, but we could also model transcendence to, let's say, a collection of agents or even abstract concepts and so on. So yeah, these are some of the things which we plan to explore in future. We have been working on this project along with Janvi, Karthik, and Nikita, and they have been doing some very excellent work. And yeah, it has been some great experiments and simulations. So yeah, thanks a lot to them. And we would also like to acknowledge Minro here for their support on this project for us. These are our publications related to this topic, and you can refer these for further details and more detailed results and so on related to computational transcendence. Yeah, with that, I'll conclude. Thanks a lot for listening, and now we are open to questions and comments. Thank you.
Thank you, Jayati. We are open for questions now.
Thank you, Jayati. I think we can open up for questions.
Yeah.
I think there are some questions in the chat. Professor Sujit is asking, can this idea of transcendence, computational transcendence, be used in communication networks for routing protocols?
Yeah, I guess when the agents when we have transcended agents, they can take the network flows at the system as a whole, rather than looking at just how much load they have at the individual node itself. And I think because of that,
just sorry to interrupt. I think Jayati, are you
so in fact we are in fact looking at intelligent networks
excuse me, sir.
because of transcendence. That is, currently what happens is routing happens based on rules which are defined, and there are of course some variations like cognitive radio and so on, where each router acts autonomously and may decide not to route and so on, right? And so that's where these questions that we post in the framework come up. That if I act responsibly, I incur a cost, but because I incur a cost and I don't act responsibly, then there is a collective cost that comes in. So I think the nature of the transcendence can actually help in better adaptive networks to take kind of.
I think Jayati, your answer was
okay, I think there's one more question by Professor Vidisha. I think she has raised her hand. So Vidisha, you can go ahead.
So my question was maybe more in relation to the future work that you're doing in this. So when we talk about transcendentalism in the context of institutions, there is this. It comes from the assumptions that we cannot most of the time pin down an ethical behavior to a specific individual. Hence, we need to have some sort of institutional setup and the procedures in place to sort of transcendence this one but individualistic understanding of accountability to collectives. So in that sense, what I was thinking that in the current scenario, where the regulatory or the institutional framework, which is kind of lagging behind the technological innovation, right? So when you're trying to build a responsible agent, you are necessarily trying to hard code the values, certain values, and trying to see that in what extent these values can be, lead to kind of an elastic understanding of self. That means that it's not completely hard coded, these values. So my question is that how do you also kind of balance the question or trade off the question of accountability with this responsible agent? What do I mean by this question of accountability is that to what extent we can attribute an unethical behavior, so-called quote-unquote unethical behavior, to this specific agent. And if we are able to, let's just assume that we are able to very clearly attribute an unethical behavior on part of this agent that you're trying to build, who will be accountable for this unethical behavior? When we do not have this, institutional or the, we cannot transcend it. Does that make sense? The question makes sense?
Yeah, thanks, Vidisha. I think it's a very interesting question. Would Jayati like to take a shot at addressing this?
I would say the agent is still accountable when it is doing any action. Just that what we're saying is with the elastic sense of self, it will take actions which are more aligned to the collective, but it will still be accountable for whatever action it does in that context.
Yeah, I think in an organizational setting as well, right? When we say somebody is acting unethically and so on, right? And most of the cases, at least, they're acting in self-interest, right? They're acting for their own, for example, collusion, corruption, and so on. They're trying to maximize their self-interest, right? Which may not necessarily be the institutional interest, or it may not be the collective interest, and so on, right? And so they are in fact acting rationally, okay, but not responsibly in this. There are institutional mechanisms like incentives, disincentives, which is what I mentioned. Reinforcements, external reinforcements to bring discourage such behavior and so on. On the other hand, what we are trying to explore is that there could be some innateness to help emerge a responsibility from a bottom-up fashion. So for example, we could an employee could act ethically out of a fear of reprimand, or out of a fear of some kind of backlash from the system, or an employee could act ethically because the employee kind of identifies with the institution. The employee feels that the institution's success is one's own success to some extent. The employee feels gratified with the institution's success. The employee feels concerned with the institution's failures and so on. Right? And, so the positive or negative payoffs that the institution is getting, the employee is also deriving certain kinds of utility from that, right? And so this is where we get a shared set of ownership once it develops in an institution. We are basically claiming that such institutions can be more resilient, because the externalized mechanisms for bringing responsibility can become very complex, while these can be much more adaptive and resilient.
I have a follow-up, but
I
I'll
hope
come
that
back to
kind
it
of answered
later.
the question. There's also one more question on the chat. Okay.
But I can come back to it later because I see there are already two more questions. So I'll
Okay, yeah, maybe I can take the next question. Professor Amit is asking that does your model also incorporate an understanding of context influenced and shifting nature of values? For example, what I value for myself may change depending on the context. Similarly, what I value in my relationship with my family, team, or society, etc., might keep shifting. So very true, actually. And I think the transcended agents are able to do that by updating their semantic distances to each of the aspects they identify with. So after the interactions in the system for some time, they update their semantic distances and to each of the aspects, right? So individually to, let's say, their family, to their teammates, to the society, based on their interactions with the system, they can decide on what their assumptions were of the semantic distance. Are they correct, or should they update it? And in one variant which we discussed, even the transcendence level of the agent itself, right, it is able to update that based on their interactions.
Yeah, just to kind of expand on this, there are two levels of elasticity here. One is we have a extent of elastic self, but then how much we attach this elastic self to different objects may vary. Some of them may identify very closely with their ethnicity, with their religion, with their nation. Some of them may identify more closely with their family, institution, whatever. And so this distribution can change, can be different, and also can change over time. So that is how we kind of vary those distances. And second, like she was mentioning, the elasticity levels itself may change. Over time, we may become more elastic and more or less elastic, depending on our experiences. So we may start identifying more. That's the gamma interactions that we are seeing. So both are possible in this.
Yeah, there's a question from Prasida. How do you find these values organically, just to understand the behavior of the system?
Can you take the question?
Right. So yeah, again, it is based on the interactions. We start with some initial levels of, let's say, transcendence, the semantic distance to different attributes, and then based on how the interactions have been, right? Based on that, the agents are able to update their behavior and the transcendence levels and so on. So yeah, so we start with some notions of initial transcendence level, and then it is updated based on their interactions. Yeah, hope that answers Prasida's question.
So my question was not so much about how to bring in accountability from an external source in an abstract form. I wanted to ask that, right now there are no strong or robust institutional framework to understand what is expected out of an autonomous moral agent. Like, for example, when I am an employee of an organization, there are certain rules and protocols or standards in place that I understand that is expected, and that's how we frame our responsibility. And this is true across different roles that we play, like whether in terms of my family or in terms of my professional um, you know in my peers, among my peers, or even at an institutional level. But given that the technology is sort of leapfrogging at a much faster pace in comparison to the policy or the regulatory framework that we have in place. So in that vacuum, my question was, when you are trying to create these moral agents, how do you anticipate that to sort of, fill that void? That you're literally like what we are trying to do right now is to take reference from what we know with our existing institutional framework and draw this understanding of what it means to be responsible or what it means to be accountable, right? So it's a very clear human reference that we are using, or human institutional references that we are using. So do you think that our policies would somewhat have to then catch up with this, or we have a sense that there is a void, that there is no institutional framework to guide these autonomous agents if they falter? So there is no consequence for them at the moment. So that's what my question was.
Yeah. Okay. Yeah, I guess I understood it. I think a very valid point in the sense that, see, like you mentioned, right? If the landscape around the technology landscape, for example, is fairly stable, right? It becomes fairly straightforward for an organization or institution to say, this is what we do, that's it, right? And then uh, percolate down some rules and expectations and so on. Okay, this is what we do, this is what we expect everybody to do and so on, right? But more and more, as you likely said, the technology landscape is changing so fast for organizations today, especially, post 21st century and so on. It becomes very difficult to kind of set a very clear expectation, to all the employees, saying that this is how exactly the organization will work and so on, right? And it is exactly in these cases where the idea of transcendence, in my opinion, can become much more relevant, because we do not know, because there is uncertainty in the external world as to what exactly we do, rather than uh, rather than speaking in terms of, say, accountability and consequences, right? We are basically trying to see if we can we can speak in terms of a collective identity, right? So we do something, let's say the collective improves, and we all improve. We do something and the collective faces a hit, we all face a hit, and so on, right? And so if we are kind of transcended, to the collective and so on, right? And so in a sense, now in today's world, especially what's happening with the very fast changing landscape is that organizations, agile organizations, are becoming more like a collective identity of all its employees, and the employees are working together to they're not reporting to one another in the sense, so they're basically working together to realize the potential of the organization. So there is this quote from Akio Morita, the founder of Sony. This was in a different context, but it's kind of relevant here. That he was comparing organizational principles between the US and Japan, or Asian approach to organization and so on. And basically, what he was saying was in the West, the axiom is that if your employees are happy, then they're productive, and so on, right? So therefore, you should keep your employees happy, which will make them productive, right? And while in Asia or Japan, where he was talking about, he was basically saying that if we are productive, then we can be collectively happy. That is, if we are productive and the company is doing good, then collectively we can be happy. So here the collective happiness of all the employees is the goal, and productivity is the means to that goal. While in some other paradigm, productivity is the goal and happiness is a means to that goal. So in this sense, this is more of the Asian paradigm, in this the kind of thing that we are looking at.
Thank you for the response. I think it clears my doubt.
Then let's maybe in the interest of time, we'll go to the next question as well. There is one more by Professor Amrita. There exists, as we see, there exists a trade-off between the cost and ratio of packets dropped for a particular application, right? So is there a way we can theoretically compute optimal values of transcendence and other system parameters which can help us? Very good question. We, as of now, we can compute that for very simple networks. Maybe a star network. What would be the transcendence level for? We can compute some kind of bounds. But for arbitrary complex networks, it becomes very difficult to find that bound. So that's why we are trying to estimate this empirically. So which is what we saw in the second part of this, where transcendence levels can be discovered, right? Optimal transcendence levels. So maybe if you can go to that slide, which shows. So basically, we initialize the network with arbitrary initial transcendence levels around 0.0, let us say. But even then, they come and settle down to somewhere like 0.6, right? So this is the optimal bound that they have found. But then if the initial levels are itself around 0.6, we see that they have come and settled down to even much higher transcendence levels, with much lesser variation in this. So basically they're discovering what is the optimal level, but it's in an arbitrary network. So this was a random graph that we generated using the Erdo-Shreni model. So for random graphs like this, computing a theoretical bound, we still don't have a closed form solution. So yeah, I hope that kind of answers this question. Great. So yeah, I guess we are done. If there are no more questions, maybe I can hand it back to the chair to take over from here.
If there are no more questions, I think we can conclude the session today.
Yeah. Thanks again, Jayati and Professor Srinath, for the wonderful talk, and we'll close the session now.